So we left off the last video where I showed you these so-called angular scaling factors. These are basically quantifications of how much overlap there are for sigma bonds and pi bonds potentially for the different d orbitals in different positions for the ligands, which can describe, in this case, a lot of the different coordination geometries. So now what we're going to do in this video is actually show you how you can use this table, which I will always give you. Okay, obviously you don't have to memorize this. It's one of the handouts that's posted online. I'll give it to you in an exam if you need it. And so, right, here I'll also give you this little nice table, which tells you, hey, if you want to make a trigonal bipyramid, use positions 1, 2, 7, 8, 6 for the ligand. Kind of makes sense. You could probably figure this out yourself. But here's 1, 2, right, 7, 8, and 6. So 2, 7, and 8 together make a triangle. That's the equatorial triangle of a trigonal bipyramid. 1 and 6 are the axial sides. And you can go through this and use the other ones. All right, so let's do an example. The example I want to do is figuring out whether or not, or looking at the energies of octahedral complexes versus tetrahedral complexes. So what we're going to do is we're going to first calculate the octahedron. And this handy table tells us that we better use positions 1 through 6. Make sense? So we're going to do this for every position and for sigma and pi bonding interactions, which we call E sigma and E pi, for all the 5 orbitals. So first, let's do the dz squared. So E sigma. E sigma, how do we calculate that? Well, for dz squared, all we're going to do is add up all the E sigma values for positions 1 through 6 under z squared. So it's going to be 1 plus 1 quarter plus 1 quarter plus 1 quarter plus 1 quarter plus 1. That's for sigma interactions. Okay? And so that is equal to 3. And so we have a value of 3 sigma so far. And then we're going to do the same thing for E pi. And you can see that is all these zeros here, z squared. There actually can't make any pi interactions here. Okay? So E pi is going to be equal to 0. All right, so far so good. So what does that mean? That means the total energy of the dz squared orbital is 3e sigma. Why? Well, it's 3e sigma plus 0 e pi. 0 e pi, so it's just 3 sigma. Okay, and so we go through this, okay, and do it for all the orbitals. X squared minus y squared, guess what? You also get the same number. Why would that be? Well, we know that the EGs are degenerate, right? dz squared is degenerate with dx squared minus y squared. So we better get the same answer. You can go through it and see if you want, but very quickly, position 1 through 6 for x squared minus y squared, you're going to get 0 plus 3 quarters plus 3 quarters plus 3 quarters plus 3 quarters plus 0. That's going to get 3 sigma, and there's zeros across the board for the pi's, so that's going to get you 3 sigma. So you do this for xz, yz, and xy, and lo and behold, as we expect, we get those are triply degenerate. They all have the same energy, and they have the same energy as 4e pi. So this is kind of cool. That tells us now, in terms of sigma donating and pi donating / accepting abilities of ligands, what the energies are of the d orbitals and what the gap is, the delta O between these two, right? Which we know is relevant for a lot of different processes, including absorbing light, which gives rise to the colors of transition metal complexes, right? The DD splitting. So delta O is going to be just 3e sigma minus 4e pi. We do the exact same thing for tetrahedral. How do we do it? Well, we go through here, and now instead of using these octahedron values, we use the tetrahedron parameters. So we use spacings 9, 10, 11, 12, position 9, 10, 11, 12. We use this chart. We go through, look at the 9, 10, 11, 12 region, add them all up. I'm not going to do that for you because it's just kind of a waste of time, and I know that you can add them, okay, and read the table. It's pretty easy if you're just careful with looking at the table, right? But if you do that and check to make sure that you can do that and you get these values, these are the values you will get, okay? And remember, the XZ, YZ, and XY, those are the T2s in tetrahedral TD symmetry, are higher in energy now than the E's are. Okay, there's this flipping that occurred. And very interestingly, we can actually show this relationship that I showed you before, that delta O equals 4/9 of delta T. Okay, this is defined as delta T, of course. Why would this be higher in energy? This 4/3 E sigma plus 8/9 E pi term, why would that be higher in energy than this term? Well, remember, E sigma is always much higher than E pi because pi bondings are stronger than sigma bonds. So this term is higher than this term. 3 sigma, you better believe, is higher than 4 E pi because E sigma is usually like 4 or 5 times roughly stronger, okay? So delta T. Delta T is equal to 4/3 E pi plus 8/9 E pi minus 8/3 E pi, right? Just the difference between these. That's what I have written out here. Okay, so we can combine the E pi terms. That gives us 4/3 E pi, 4/3 E sigma minus 16/9 E pi. And some fraction, least common denominator work, right? What is very interesting about this is then you can factor out a 4/9, okay? If you factor out 4/9, you're gonna get 4/9, delta T equals 4/9 times 3E sigma minus 4E pi. Well, guess what 3E sigma minus 4E pi is? That is the definition of octahedral, which we talked about just a while ago. So that tells us this formula that quantitatively, rigorously, delta T is 4/9 delta O. And so, that wasn't coming out of thin air. That came out of the geometries and the amount of overlap that can happen between the different d orbitals in these different geometries as a function of pi bonding overlap and sigma bonding overlap, right? And remember, this delta T being, about 44% that of delta O had ramifications. It meant that most tetrahedral complexes are going to be high spin because now you have a much smaller gap than in octahedral complexes. And so that means it's going to be much more likely to populate electrons, much more favorable to populate electrons in a higher energy state, these higher T2 states, right? Because who cares? Because because you're not populating them up that much higher, right? So the penalty you pay for pairing them is very high in this case. So low spin tetrahedral complexes therefore are very rare. All right, so in the next video we'll do another example and go in really in depth about how to use this actually for different d electron counts to predict what different coordination geometries are going to be preferred.